Today we're going to talk about a new number called E. E is a really important number in math. It's similar to pi, where it's a symbol that stands for a number, but in this case, E is a number that stands for 2.718281, so on and so forth, ... Just like pi, it goes on forever, right? E is associated with exponential functions and log functions, of which we're very familiar with. And it's used a lot in life when you're talking about interest, relationships with money, when you're talking about mortgages or car payments or credit cards and so on. So it's something that you want to be familiar with when you're getting used to spending money and saving money and things like that. So the first thing we're going to talk about here is we're going to go back to our normal y equals b to the x exponential function formula. But instead of having b as any base being a number of like 1, 2, 3, 4, or something like that, we're going to replace b with the number e, which again stands for 2.718281, so on and so forth, right? So we rewrite our exponential functions as y equals e to the x function. But if you remember, a generic exponential function is y equals a times b to the x. And sometimes we ignore the a, quote unquote, ignore the a when the a is 1. So this case right here in this blue formula here, it really means y equals 1 times e to the x. Okay? So what we're going to do first is graph an exponential function where e is our base. They already have the graph made for us, but I want to remind you all what this formula, everything in this formula means and how to graph it. So remember our a value here, a value, is our y-intercept. So there's our y-intercept. We have x and y. I'll make a little table here. Our y-intercept is 1. That means when x is 0, y is 1. And that's indicated on our graph right down there, okay? We can plug in any other number for x. We can choose anything. I'm going to choose 1 for x. And how is that going to look in our function is it's going to be y equals, because we have to figure out what y is, 1 times e to the first power. And again, we remember what e is. We're going to go back up here. E is 2.71, blah, 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 blah. So I'm just going to simplify it as 2.7. So when we have 1, I'll get this a little bit bigger. When we have 1 as our x, our e is 2.7-ish. There you go. Okay? So that's just an introduction to how to graph e, and as an exponential function where e is our base. And this represents a growth function. Okay? Because our base is greater than 1. Now, if we have a growth function, I'll say this growth function is represented, that looks like a graph like this. And we were talking about a growth function being y equals e, again, which is 2.71 to the x power. What does a decay function look like? A decay function would be the inverse of a growth function. So that formula would be y equals 1 over e to the x power. And what would that graph look like? Just a very rough sketch would be the opposite. It would look like it was decreasing or going down like that. Okay. I'm going to move on to page 2 here. And when we talk about the number e in log format, we're going to mention it in a different way than what you're familiar with. We're familiar with the common log form being like log base of something to a number. So for example, this generic example right here is log of x, which is the same thing because there's officially the base is not indicated, but when there's a base not indicated, that means it's log base 10 of x. Well, the natural log is what we're going to call log with the base of e. Okay? So natural log is indicated by this term ln. That's not an I, that's an L. So ln. So when you see ln, you know it means log base e. Okay, so again, ln is the exact same thing as log base e. And just to remind you one more time, e is a number, 2.718, blah, 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 so on and so forth. Okay, so let's practice how this is on the calculator. Well, here is our normal, this is a common log example. We know how to plug this in the calculator. All you do is you push the log button and you put 8. Log of 8. This is, of course, log, when you just push the normal log button, it's log base 10. We know that. So what is log of 8 when you put it in your calculator? 0.903. But now, when we're talking about the natural log, which is, again, this is the exact same thing as log base e of 0.3, you could go in and do math alpha math and put log base e in there, but there's a button immediately underneath your log button that says ln. That means log base e. So just practice on your calculator. What is ln? 0.3. And when you push ln 0.3, you're going to get negative 1.204. Okay? Here's another one, ln 0.75, 0.75. So again, ln means log base e, 0.75. But in your calculator, you're just going to push ln 0.75. And what does that equal? Negative 0.288. Okay, pretty simple. It's nice that your calculator has a button that's just ln. Okay, so as we know, logs and exponents are cousins, right? Or they're inverses of each other. So here's some examples of some problems where we want you to simplify, where we don't have a variable. We only have e in here as our I don't know, magic number in these problems. Okay, so how do we simplify this? If we remember our properties of exponents, this 3 on the outside is going to be given to the 2 and given to e to the third power. And so what does this end up being is 2 to the third power times e to the what? To the 9th power. You got it because you multiply the two exponents. We can simplify that down even more. 2 to the third power is 8. And then e to the 9th. We're going to keep e to the 9th because, again, if we plug that in our calculator, it's going to give us this big, giant decimal number. We're just going to keep it as 8 e to the 9th. Okay, that's the most simplified and that's the most accurate number we can get. How do we deal with e to the 5 divided by e to the 2? Okay, well, if you remember our relationships, when we have a division situation, we're going to do e to the 5 minus 2. So this becomes e to the third power. Okay. This guy over here, 10 e to the second, over 2 e to the fourth. I'm going to do this. I'm going to do a little I like to put a little wall in between there just to separate those. And what's 10 divided by 2? What is 10 divided by 2? Oh, we know that. That's 5. Okay, put a little equal sign there. And then what's e squared over e to the fourth? Well, you can do e2 minus 4. Or you can just say there's 2 up top and there's 4 in the bottom. 2 of them will cancel. So in the end, this is going to end up being 5 e to the negative 2. Or, more officially, 5. We're going to bring that e to the negative 2 downstairs over e squared. What are we on? Number 4 here. We have a 2 on the outside. I'm going to bring this in. I'm going to distribute it to the 5. And I'm going to distribute it to this whole situation because this is e to the negative 3x power. And so the 2 is going to be distributed to the 5. That's going to give us 5 squared. And then e to the negative 3x times 2 is negative 6x. Okay? So that's going to end up being pretty... It would be negative 2 on e5 e to the negative 6x power. Okay? If we bring that downstairs, the negative 6x, that's going to end up equaling 25 over e to the positive 6x. Okay? E squared times E. What do we do when we multiply two things with the same base? When we multiply, what do we do to the exponents? Is we add them. So this is going to be e to the 2 plus 5, oops, which is e to the 7th power. Okay. And our last one, 12e to the 4th divided by 3e to the 3rd. I'm going to again put this little, I just like putting a wall in between there to know how to deal with these two separately. What's 12 divided by 3? 4. And then what's e to the 4th over e to the 3rd? I can do my e to the 4 minus 3, which is e. Or I can say there's four e's here. Oop, 4 e's here, 3 e's here. The 3 cancel, so it would be 4e left over. Okay. This next bit we're going to evaluate, which means we're going to get an answer for each situation. I'm going to change colors here. I'm going to do my f of x, I'm going to do in blue, my f functions here, and g of x, maybe I'll do those in green. Okay. So the f of x function is 2 times e to the x plus 2 power. Now when we want to evaluate, we're going to use our calculator. You're going to use your calculator, but let's figure out how to use the calculator to get e to some power. Right? What you're going to do is you're going to use the second button. You're going to touch the ln button after that, and that's going to give you e to the x power. Okay? So in our first situation, when we have f of 1, we're going to take the 1, we're going to plug it into everywhere we see x in our f of x formula. Okay? So that's going to be 2e to the 1 plus 2 power, or in other words, 2e cubed. So how do we plug that into our calculator? We're going to do this part first. Makes it a little bit easier. I'm going to hit second, ln, 3, and then multiply by 2. And what does that get? That gets us, looks like 40.171. We'll try it for f of 0. So f of 0, we're going to plug in 0 for x. So 2e to the 0 plus 2 power, which is the same thing as 2e to the second power. I'm going to plug in my calculator, second, ln, 2, and then multiply by 2. We get equals, what is that? 14.778. The one last one, ooh, now we got a negative number. This is great. 2e, I'm going to plug in negative 3 to my x, plus 2, which gives us 2e to the negative 1 power. And what does that do when we put it in our calculator? Second, ln, negative 1 times 2. That gives us 0.736. Okay, let's move on to the g of x function. We're going to do a couple of practice problems on that one too. G of 1, we're going to plug in 1 for where x is. 6 times e to the 3 minus 1, which is the same thing as 6e squared. So I'm going to plug it into my calculator. Second, ln 2 times 6. What does that give us? 44.334. Okay, we're going to plug in now the next one, g of 0. So plug in 0 for x. 6e, 3 minus 0, which is the same thing as 6e cubed. Plug that in the calculator again. Second, ln 3 times 6. And that gives us 120. Wow, it's going up pretty fast, isn't it? It's because it's still an exponential function, so things are increasing pretty quickly. And then g to the negative 2. So g to the negative 2 power, 6e to the 3. Be careful here because it's a 3 minus x, so we have to have 3 minus 2, which makes plus 2. So that gives us 6e to the 5th power, right? So that's going to give us a big number when we plug it in our calculator. I'm assuming a big number. Second, ln 5 times 6, which equals giant 890 point, what does it say, 479. Okay, so there's just a couple things showing you how to calculate use your calculator, use the the second ln button to get e to the x power, and then you can plug in whatever you want for x. Okay. Next page here, we're gonna do our favorite. We're gonna graph. Okay, so we're gonna graph some exponential function. I'm gonna do my f of x. I'm gonna use red. My g of x. I'm gonna use green. And then my h of x, I guess I'll pick blue. Okay, so exponential functions, we know from page 1, exponential functions, where we have growth. So my base is greater than 1. It's going to look something like this. Okay, oops, it's kind of messy. And with growth functions and exponential growth functions, our asymptote is going to be a y equals thing. And just like with log functions, you can kind of look at the formula or what you have here and kind of see already what your asymptote is. I'm going to tell you right now, it's whatever was plunked at the end. Here's my asymptote there. There's my green pen. This one, there's my asymptote here. And then the blue one, there's my asymptote there. All right, so that's nice. It's really nice of them to do that. Make it easy for us. What I'm gonna do is I'm gonna make a grid here. Here's my 0 line, my x-axis. I'm gonna make my y-axis, I don't know, right here. Y-axis. And we're gonna start graphing them. I'll start with the red, the f of x, okay? So with my f of x function so far, I know my asymptote is y equals 2 because our growth function has a y equals asymptote. Okay, so let me just do that. Y equals 2, make that one here. My asymptote. And then I'm just gonna start plugging in numbers for x. The first number that's really easy to do is I'm gonna plug in 0 for x. So we're gonna have 3 times e to the 0 power plus 2. What is anything to the 0 power? Is 1. So 3 times 1 plus 2 is 5. Oh, look at that. There's our y-intercept. Okay. So we're gonna have, I'm gonna plug this in here, 0, 1, 2, 3, 4, 5. There's our first point. And then I'm gonna plug in 1. Okay, what's 3 e to the first power plus 2? Well, what's e to the first power? It's 2.71, blah, 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 right? So I can just take my calculator and go 3 times e, so 3 second ln, okay. And add 2, and what does that give us? 10.1. I think I might go off on my graph on this. So 1 over, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right above here. There we go. Okay, and then actually I'm going to put in a negative number because it's always good to do a negative number. Now a negative number, 3 e to the negative first power plus 2. Plug that into our calculator, and we're going to end up getting 3.1. We do e to the negative first power, so second ln negative first power times 3, and then plus 2. And that ends up getting 3.1, like I said. So negative 1, 3.1, where are we? 3.1's right there. 1, 2, 3, like this. And that's already a good start for our graph. So we'll just end there with this graph. And I'm gonna know, I know my asymptote is at y equals 2, like this. And it goes on forever, this way and this way. And let's now get domain and range. Awesome thing about domain and range here, for exponential functions, excuse me, domain is all real numbers. Boop, 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 boop. And then the range, this is based off of your asymptote. Whatever your asymptote is the bottom of your, or the bottom of your range. So my range here is y is greater than 2. You can also say 2 less than y less than infinity, either one. All right, let's do the green function, which is what, g of x, right? So we have g of x. What's our asymptote? Let's see, I'll put it over here. So we have x and y. Our asymptote is y equals 1. asymptote, so I'm going to do that. Y equals 1. I'm going to plug in the same numbers, 0, 1, negative 1. What do we get when we plug 0 in now to our g of x function? 3 times e to the 0. Again, anything to the 0 power is 1. So really this is 3 plus 1, 4. Okay, I'm going to plug in 1. So 3 times e to the first power. E to the first power is just 2.71, blah, blah, blah. So 3 times that plus 1 gives us 9.15. And then I'll plug in negative 1. So 3 times e to the negative first power plus 1. Use my calculator for that. And I get 2.10. Okay, so let's go ahead and graph those. So 0, 4, 1, 2, 3, 4, 1, 9.15, 1, 2, 3, 4, 5, 6, 7, 8, 9.15 is about here-ish. And then negative 1, 2.1 is about here-ish. And then we know it follows our asymptote. There's our g of x function. What's our domain and range of our g of x function? Domain, just like our red function or the f of x, all real numbers. And the range is based off of now the green's asymptote, which is y is greater than 1, or you can always say 1 is less than y, which is less than infinity. Okay. The last one we're going to graph is our blue one. Make a table of values for this guy. We're going to do the same numbers, 0, 1, negative 1. And we already know our asymptote here. Our asymptote is y equals 2. Oh, it happens to be the same as the red one, but that's okay. It's going to look a little different because this is not 3 times x times e to the x, so it doesn't have a stretch or compression. We're going to go ahead and start plugging it in. What's e to the x? I'm sorry, when we plug in 0, what's e to the 0 power? 1. So 1 plus 2 is 3. So I'm going to do that right 1, 2, 3 right there. When I plug in 1, I have e to the first power, which again is like approximately 2.7 plus 2, so that's about 4.7. Okay, 4.7, 1, 2, 3, 4.7, that's about here-ish. Okay. You can already kind of see how like it's going to get a little wider. And then negative 1, when we plug in negative 1, is e to the negative first power, which is 1 over e to the first power, or 1 over 2.7 plus 2. I'm definitely using my calculator for that. That's going to be 2.37. That's a 2. Negative 1, 2.37 is maybe about here-ish. And then we know it's going to follow our asymptote. There you go. There's our blue function. So our domain in our blue function is the same as the green and the red, all real numbers. And our range is based off of our asymptote, which is y is greater than 2, or I can say 2 is less than y, which is less than infinity. Awesome. All right. So we're good with that. Let me move this page up here a little bit. Now we're going to jump into something you guys did in your homework the other night, I think last night it was, is using the change of base formula. Just a real quick reminder. Here's my change of base formula, change o base formula. If I have a log of a to the b, that is going to give me, I can pick any new base, whoops. I'm going to pick log base 10, just because, and that gives us log base 10 of b over a. So that's our formula. So we're going to follow that with these guys here. And just, you could really plug in log base 26 of 9. That's going to be the exact same answer as when you use the change the base formula. But we want you to get in the habit of using change the base formula to get these answers, because sometimes you need to use it to solve. So this one, I'm going to change my base, log base 10, log base 10. I don't really need to write the 10, because remember, just if I just said plain old log, that would mean log base 10. But log of 9, because that's this guy right here is my b according to my change of base formula. and then log of 26. Okay, we'll do this next one. Log of 30, you get the top number on top, or the big number on top, over log 12, and so on and so forth. Okay, we'll do this one, log 0.1 over log of 6, and then this guy, log of 9 over log of 4. Okay, so that's what we're going to do, just change the base. We're just practicing change the base formula there. Okay, that's pretty straightforward. You did that in your homework last night, so that's great. Ooh, now we get to the good stuff. Not that the other stuff wasn't good, but. So I mentioned in the beginning that E is used frequently in real life, in investments and in calculations of interest in banking. And so it's really important to know there are a couple different ways that E is used, again, in the financial industry. And when you put money into a bank account, there's multiple different ways that you can gain your interest. You can gain it on a continuous level. Oops. Let me put my pen going. On a continuous level, which is like this guy here, the continuously, or you could gain it on a different level, which could be daily or monthly or weekly, and we'll get to that in a little bit. But if you're reading any form of interest statement and they say your interest is compounded continuously, what they're doing is they're using E in their equation to calculate how much interest and how much money you're going to get in the end. All right, so there's this formula here in the red formula. You got A equals P times E to the RT. I'm going to put a little dot in between the P and the E, because it's only E, again, which is a number, 2.71, blah, blah, blah. Only E is raised to the R and the T, okay? Let me define what each one of these values mean, or each one of these variables mean. Now, E, again, is not a variable, so E itself is 2.7, so it's not defined in these variables here. But A, this guy right here, is your is your amount that you're going to get after you've collected all your interest. So that's your final amount. That's like the goal. I want to like put a bunch of money in and make a bunch of money. You know, it's like how much you're going to make in the end. P is your principal value, or it's the original or the initial or the starting amount of money that you're going to put into your bank account. I think when I was a kid, I put $5 into my first savings account. R is your interest rate, and your interest rate is usually given to you in percentage, but we have to convert to a decimal in order to use it in this formula, okay? So we convert it into the decimal. We're going to move the decimal 2 spaces to the left. I'll get to that in a second, okay? And then time, T is time. Time is how long you'll keep it, how long it will keep or be in the account. Okay, so let's start this by doing this word problem. There's kind of 2 problems within this one word problem here. This is the first one. I'm going to call this the A word problem, the first one. And then there's another amount of years, I'm going to call this B. Okay, so I'm going to do the red guy first. Okay, the red guy, so my first part of the problem here. How much will a $100 deposit earning 6% interest compounded continuously? There's that word, continuously. So I know I can use the formula A equals P times E to the RT. How much will it yield in 5 years? Okay, so here we go. We got $100 is our initial value. That's the amount, the starting amount of money that we're putting in. So that's our P. It's going to earn 6% interest. So that's our rate. But wait, we have to convert it to decimal. So 6% interest is the same thing as 0.06 in decimal. Okay? Compounded continuously, that tells us to use this particular formula and yield in 5 years. So this is our T, is 5 years. So what we have is A, because we're figuring that part out, we have $100 that we started with, times E, which is a number again, but we're using E, of course, to symbolize the number. And then our rate was 0.06 times T, which is 5. Okay? And the important thing here is we're going to do this guy first. So in our calculator, what is 0.06 times 5? 100 E. What's 0.06 times 5 is 0.3. And still we're going to do this in our calculator first. So we're going to hit second, ln 0.3 times 100. And what does that give us? Is $134.99. Cool. That's not so bad. $100, you end up making almost $35 in 5 years. Yeah, it's free money. That's all that matters. Okay, now the next one we're going to do is a different time. We still have the same P, the same interest, and it's still compounded continuously, but now our time is going to be 7.5 years. So let's set that up. A equals $100 is our P, times E to the R, which is our rate, 0.06, times, now our new years is 7.5 years. We're going to plug this part into our calculator first. So 100E, what's 0.06 times 7.5? 0.45. I'm going to do second, ln 0.45 times 100, which gives us $156.83. Awesome. So now you can tell how much money you're going to get after a certain amount of time. Let's do another example. Good old Joyce. I'm going to do Joyce in green. Joyce's parents create a trust fund for her when she's born, and they deposit $10,000. Oh, let me make this smaller so we still have our formula. The trust fund pays 9% interest compounded continuously. This is a really important word because now we know we can use A equals P times ERT, or PERT, call it. Determine the balance of this account when Joyce goes to college at the age of 18. So our A is what we're trying to figure out. Our P is $10,000. Our R is 9%, but we're going to turn that into a decimal, 0.09. And then our T is when she was born to 18 years. Okay? So let's set this up. A equals, what's P? 10,000 times E. E's a number, so we're going to keep E there. Times the rate, 0.09. Or not times the rate, sorry, raised to the rate. And then times 18. Okay, we're going to do this part first in our calculator. So that gives us 10,000 times E to the, what's 0.09 times 18 is, looks like 1.62. Plug this into our calculator first. Second, ln, 1.62 times 10,000, which gives us, holy moly, $50,000. $50,530. That's ridiculous. Just for sitting in a bank account for 18 years, that's awesome. So good old Joyce, she'll have a lot of tuition for college when she gets there. That's awesome. And that was, again, compounded continuously. We're using A equals P times E raised to the RT, or in other words, PERT. But you only use this A equals PERT when you have compounded continuously. Okay? Our next example, we're going to use a different formula because we're not being compounded continuously, which is in black. This is compounded monthly. Now you could have some interest accounts that compound monthly or daily or yearly or bi-weekly or twice a year or something like that, right? In this particular problem, it says monthly. But that's very different than compounded continuously. So you have to use a totally different formula. Now, here's the formula down here. P is still your initial amount. Okay. R is still your rate. Oops, that doesn't look like rate. Rate. T is still your time. But then what the heck is N? N is how many times per year your money is compounded. Okay, so in this case, I can't spell monthly. Oh my gosh, that's horrible. Monthly is 12. That's our N. Okay, so monthly is going to be 12 in this case, because again, if it said daily, it'd be 265. If it was weekly, it would be 52, and so on and so forth. But monthly, it's going to be how many times per year, which is 12. So we have A, which is what we figure out what's going to be our amount when we're done. P, what was our initial amount? Oh, $100. 6%, but 6% in decimal is 0.06. Okay, so we have 100 times 1 plus the rate, 0.06, divided by N, which is 12, because that's monthly, raised to the N, again, which is 12, times T, which is time. In this case, they give us the two options again. In this case, T is 5 years. We're going to do this one first, okay? This guy first. I'll do the slash there for the second one. That'll be times 5. So we're going to we have to be really careful doing everything individually. So remember PEMDAS. So with PEMDAS, we're going to do everything in here first, okay? What's 0.06 divided by 12? 0.06 divided by 12 is 0.005. Okay. What's 12 times 5 is 60. We still got our 100 out here. Okay. And then I'm going to I still got my 100 out here. 1.005 to the 60th power. Really important. We want to do this guy first. So 1.005 raised to the 60th power is 1.34. Now we do times 100. So that gives us $134.89. Okay. Well, let's do the next part. Let's do now over 7.5 years. I'm going to do a slash here. We still have the same situation with $100 as our P, or our initial amount. 1 plus, we still have the same rate, 0.06. We still have it compounded monthly, so N is 12. And then raised to the N, which is 12 again. And then now our T, our new T, is 7.5 years. Okay, so again, be really careful. Leave the 100 there. We know 0.06 times 12, 0.06 divided by 12 is 0.005. 12 times 7.5 is 90. We're going to do this part first. So 1.005 to the 90th power. What is 1.005? Oops, I put too many zeros there. What is 1.005 to the 90th power? Is 1.566 something. So our final answer, when we do 1.566 times 100, is $156.66. All right, that's it. Now you know how to make a sound investment, and you understand what E is, the natural log is, log base E is ln, and what E stands for.